Good morning. My name is Sakshi. Inorganic Chemistry, Semester 4th. Chapter name is Chemistry of Lanthanide Elements. We have learned that elements in which the last electron enters the f orbital of their atoms are called f block elements. In these elements, the last electron is added to the third to the outermost called anti-penultimate energy level, that is n-2f. These elements are called inner transition elements because these constitute transition series within transition series. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by filling of electrons in 4f and 5f orbital and are called lanthanides and actinide respectively. The series involving the filling of 4f orbital following lanthanum LAZ is equals to 57 is called lanthanide series. The elements present in series are called lanthanides. There are 14 elements in this series starting with cerium Z is equals to 58 and ending with lutetium Lu Z is equals to 71. The name lanthanide is derived from lanthanum, the first member of series. These lanthanides are also sometimes referred to as lanthanose. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that 4f orbital in which the electrons are added are embedded in inner shells, while 5d and 6s electron which have similar configuration are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage in their separation was to get them as oxides. However, the occurrence of oxides of lanthanides are very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. The substantial deposit occurs in Scandinavia, USA, USSR, and India. General characteristics of lanthanides. The important general characteristics of lanthanide are discussed below. Electronic structure and position in the periodic table. The lanthanide involves the gradual filling of 4f orbital. It may be noted that the energy of 4d orbitals 5d and inner shell f orbitals are closely similar, and therefore the order of filling of 4f orbital in the atoms shows quite irregularities. At lanthanum Z is equals to 57, both 5d and 4f orbital become stable due to the increased effective nuclear charge as a result of poor shielding effect of 6s orbitals. Therefore, it is observed that at lanthanum the incoming electron enters the 5d orbitals and its electronic configuration is La is equals to Z is equals to 57 Xz 5d1 6s2. However, as we move further after lanthanum, the energy of 4f subshell becomes lower than the 5d subshell, and therefore the next electron in cerium enters the 4f subshell. The electronic configuration of cerium is equals to xenon 4f2 6s2. The filling of 4f orbital continues till we reach yttrium, in which the 4f subshell gets completely filled. Now, after 6s and 4f subshell have been filled, the next electron goes to 5d subshell. The configuration of lutetium is Lu is xenon 4f14 5d1 6s2. This constitutes lanthanides. The general electronic configuration of lanthanides may be written as xenon 4f0 to 14 5d0 to 1 6s2. Physical properties. The important physical constant of lanthanide. These are discussed below. Ionization energy. The lanthanides have fairly low ionization energy. In general, the first and second ionization energy of the lanthanide increases with increase in atomic number, but the variation is small and irregular. It is clear from the figure that some deviations are observed in regular increasing order, such as for EU, GD, YB, LU. These are attributed to the stability of filled, half-filled and completely filled F subshell. The first ionization energy are of the order of 560 kJ per mole, and the second ionization energies are of order of 1150 kJ per mole. These energies are quite comparable to alkaline earth metal, especially calcium. Melting point and boiling point. Lanthanide have fairly high melting and boiling point. However, the melting and boiling point do not show any irregular trend as we move from lanthanum to lutetium in the series. Inspection of shows that the europium and ytterbium have unexpectedly low melting and boiling point. These atoms from Eu2 positive and Yb2 positive ion and result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bond. The other lanthanide atoms give 3 electrons per atom in the metallic bond. Therefore, melting and boiling point of Eu and Yb are low as compared to the values for other lanthanide elements. Density. The densities of lanthanides are low, which range between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density value of lanthanides, which increase in atomic number. Eu and Yb have unexpected low values. Heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trends with increase in atomic number. Electronegativity value. The electronegativity value of lanthanide between 1.0 to 1.15 are quite close to those of alkali and alkaline earth metal. Therefore, lanthanide are expected to form ionic compound. Electropositive character. Because of low ionization energy and electronegativity value, the lanthanides are electropositive like S block elements. Oxidation state. The common oxidation states of all the lanthanide is +3. In addition, some lanthanides show +2 and +4 oxidation state also. These are shown by those elements which, by doing so, attain the stable F0, F7 and F14 configuration. For example, Ce and Tb exhibit +4 oxidation state. Cerium and terbium attain F0 and F7 configuration respectively when they get +4 oxidation states. Cerium +4 is equals to Xe F4 F0 and Tb +4 gives Xe F47. Eu and Yb exhibit +2 oxidation state. Europium and ytterbium get 5, 7 and F14 configurations in +2 oxidation state as shown below. Europium 2 positive gives Xe 4F7 and ytterbium 2 positive gives Xe 4F14. LAGD and Lu exhibit only +3 oxidation state. These elements show +3 oxidation state only because by losing 3 electrons, they acquire stable configuration of empty, half-filled and completely filled 4F subshell. Exceptional example. Some other elements show +2 and +4 oxidation states even though they have electronic configuration other than F0, F7 or F14. For example, Sm and Tm show +2 states having F6 and F13 electron respectively, in which they have 1 electron less than half-filled or completely filled electronic configuration. Similarly, Pr and D and Dy show +4 oxidation state having F1, F2 and F8 electronic configuration. The stability of these unusual oxidation state may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than the +3 state, which is characteristic of this family. Color and spectral lines. The lanthanides are silvery white, but many lanthanide ions are colored both in solid state and in aqueous solution. The color remains same even on the change of anion. Therefore, the colors are characteristic of lanthanide ion. The color of the ions depend upon the number of unpaired electrons because it has been observed that ions containing NF electrons have almost similar color to those with 14 minus NF electrons. The different ions having NF and 14 minus NF and their colors. However, it has been observed that some di and tetrapositive ion having same number of electrons, isoelectronic ions or tripositive ion, do not have same color. For example, Sm2 positive and Eu3 positive have same number of unpaired electrons, but they have different colors. The color of lanthanide ion rises due to absorption of light from visible region of spectrum, resulting in the electronic transition within the 4F level. A remarkable characteristic of spectra of tripositive lanthanide ion is that absorption bands are extremely sharp, like band in ultraviolet, visible or near infrared regions. Many of these bands are line like and become even narrower as temperature is lowered. This behavior is in contrast to absorption bands of DT transition, which have broad absorption bands. The bands of lanthanide ion are so sharp that they are useful for characterizing the lanthanide ion. The main reason for very sharp absorption band is that the 4f orbital lie deep in the atom of these elements. Therefore, they are effectively shielded from the surrounding by the overlying 5s and 5p orbitals, and consequently the absorption band arise mainly from the electronic transition within the 4f levels. Thus, the absorption band show little dependence on the nature of ligands. In addition to FF transition, sometimes color of lanthanide ion is also attributed to FD transition. The FF absorption transition of lanthanide ion have low intensity because they are not allowed, whereas FD transitions are allowed. In contrast to FF transition, the FD transitions are allowed and hence show very intensive absorption band. For example, the FD transition observed from cerium plus 3 and Tb plus 3 are very intense. Magnetic properties. All the lanthanide ions with the exception of La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ion are paramagnetic because they contain unpaired electron in their 4f subshell. The ion La3 positive, Lu3 positive, Ce4 positive and Yb2 positive, which have 4f0 and 4f14 electrons, are diamagnetic because they have no unpaired electrons. The magnetic property of lanthanide are different from those of transition elements. As we know, the magnetic moment arises from two types of motion of these electrons. The spin moment of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of the substance is due to contribution of both the spin moment and the orbital moment. In the case of transition elements, the magnetic moment mainly correspond to the spin-only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in bond formation with the ligands. As a result, the d electrons of the metal interact strongly with the ligands surrounding the metal ion. Due to the electric field of the ligands, the orbital motion of the electron get restricted, and thereby the orbital moment of these electrons get quenched. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given as mu spin only is equals to n minus 1 whole under root, where n is the number of unpaired electrons. This relationship gives almost correct values of magnetic moment for d block elements. However, the above relationship is not valid in case of f block elements. In these elements, the 4f orbitals are well shielded from the surrounding by the overlying 5s and 5p orbitals. As a result, electric field of the ligand surrounding the metal ion does not restrict the orbital motion of the electron. Thus, orbital contribution is not quenched. Therefore, the magnetic moment of lanthanide ion is due to both electron spin and orbital motion of the electron. Thus, may be calculated from the relation mu is equals to under root 4s s minus s plus 1 plus l bracket l plus 1, where s is the resultant spin quantum number and l is the resultant orbital momentum quantum number. The theoretical and experimentally observed magnetic moment values. The magnetic moment of lanthanide depend upon the atomic number and the number of unpaired electrons for the ion La3 positive F0, Gd3 positive F7 and Lu3 positive F14. The magnetic moment correspond to spin only values. For these configuration, there is no orbital angular momentum, that is L is equals to 0. The above expression becomes mu is equals to under root 4s s plus 1. The magnetic moment may be calculated only on the basis of spin only value. Here s is equals to ns, where n is the number of unpaired electron and s is the spin quantum number half, or for 4f0 and 4f14 configuration, there is no unpaired electron and H is 0 and their magnetic moment is also 0. For For 4f7 configuration GT3 positive, the magnetic moment can be calculated on the basis of spin only value because orbital angular momentum is 0. L is equals to 0 as GT3 positive xz 4f7. Number of unpaired electrons n is equals to 7. S is equals to half. Small s is equals to 7 into half. It is equals to 7 by 2. Mu is equals to under root 4 into 7 by 2 bracket 7 by 2 plus 1 is equals to root 63 is equals to 7.9 Bohr magneton. This can also be calculated as mu is equals to under root n plus 2 7 into 7 plus 2 is equals to under root 63 is equals to 7.9 Bohr magneton. The magnetic moment of tripositive lanthanide ions, the La plus 3 and Lu plus 3 are magnetic, no unpaired electron. It is observed that value increases up to neodymium and then decreases to 1.47 for Sm3 positive ion. It increases again and reaching a maximum value for dysprosium and holmium. Thereafter it starts decreasing and becomes 0 for lutetium, which is diamagnetic. The unusual shape of curve arises when the F subshell is less than half full and the spin and orbital magnetic moment work in opposite, but when the F subshell is more than the half fulfilled, they work together. Ionic radii contraction. Ionic radii, the lanthanide contraction. We know that as we move down the group, atomic sizes, covalent or ionic radii normally increases. This is mainly due to additional cells or electrons between the successive periods. However, as we move across a period from left to right, atomic size decreases. This is attributed to increasing effective nuclear charge, as a result of which the outermost shell of the electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metal increases from lithium 1.23 angstrom to cesium 2.35 angstrom, and for halogen from F 0.72 angstrom to iodine 1.33 angstrom. If we consider ionic radii of lanthanide, we get very interesting observation. For comparison's sake, we can take ionic radii of trivalent ion M3 positive, which are more stable. It is clear that ionic radii decreases from one element to another in the lanthanide series, but decrease is very small. It has been observed that from Ce3 positive to Lu3 positive, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to elements of other groups and periods. Similarly, on moving from cerium to lutetium, the atomic radii also decreases from 1.65 angstrom to 1.56 angstrom, and then decrease is only 0.09 angstrom. The small steady decrease in ionic or atomic sizes of the lanthanide elements, which increase in atomic number, is called lanthanide contraction. Causes of lanthanide contraction. In lanthanide series, the 4f electrons are being added one at each step as we move from elements to another. The shielding of one f electron by another from the nuclear attraction is quite weak due to shape of the f orbital. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of the atoms and ions. The sum of successive reduction gives the total lanthanide contraction. The consequence of lanthanide contraction. The lanthanide contraction has very significant effect on the relative properties of elements which precede and which follows the lanthanides in the periodic table. Some important consequences of the lanthanide contractions are given below. First is steady decrease in size. There is irregular decrease in the ionic radii of lanthanide. Second is electronegativity. There is slight regular increase in the electronegativity of the trivalent ions. Third, electrode potential value. There is a small but smooth increase in standard electrode potential values E0 for the process. M3 positive plus 3 electron gives M. For lanthanum, minus 2.52 volt to minus 2.25 volt for lutetium. Fourth is resemblance of second and third transition series. The lanthanide contraction affects the chemistry of second and third as we there is regular increase in size from scandium to yttrium to lanthanum. Similarly, we accept normal increase in size in other groups. Titanium to zirconium and zirconium to hafnium, vanadium to niobium and niobium to tantalum, etc. However, after lanthanide, the increase in radii from second to third transition series almost vanishes. The pair of elements zirconium to hafnium, niobium to tantalum, and molybdenum to tungsten, etc., possesses almost the same size. The properties of these elements are also very similar. As a result of lanthanide contraction, the elements of second and third transition series resembles each other much more than the elements of first and second transition series. Fifth, similarity among lanthanides. Because of very small change in size of the lanthanide and in lanthanides, their chemical properties are very similar. Therefore, their separation becomes very difficult. Recently, method based on repeated fractional crystallization or ion exchange techniques, which takes the advantage of slight difference in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size difference of their trivalent ions have been used. Sixth, basicity differences. Due to lanthanide contraction, the size of lanthanide ion decreases regularly with the increase in atomic number. As a result of decrease in size, their covalent character between Ln3 positive ion and OH negative ion increases. Therefore, the basic strength of hydroxide decreases with increase in the atomic number. Thus, LaOH thrice is the most basic while LuOH thrice is least basic. The basicity difference in the lanthanide are reflected in A. Increasing tendency to get hydrolyzed due to decrease in basic character. There is slight increase in degree of hydrolysis in solution from La3 positive to Lu3 positive. Example, La3 positive ions are less rapidly hydrolyzed than Lu3 positive ions. The thermal decomposition of oxysalts. More basic oxysalt decompose less readily. Example, LaNO3 thrice decomposes with difficulty and is less stable, where LuNO3 whole thrice is unstable and decomposes readily. Solubility of salt. Lanthanide hydroxide precipitate at regular decreasing pH value from La3 positive to Lu3 positive. Example, LaOH thrice at 7.83, GDOH thrice at 6.83, and Lu3 positive at 6.30, all from nitrate solution at 20 degrees Celsius. 7th, size of YB, HO and DY. Due to lanthanide contraction, the radii of YB3 positive is comparable to heavy lanthanide TB, DY, HO and ER. Therefore, they occur together in natural minerals. 7th, reactivity of lanthanides. All the lanthanides are highly electropositive metals and have almost similar chemical properties. This is due to the fact that lanthanide differ only in the number of 4f electrons. Since these electrons are very effectively shielded from the interaction with other elements by the overlying 5s, 5p and 6s electrons, they show very little difference in their chemical reactivity because of their similar chemical reactivities. Their separation from one another is very difficult. The lanthanides are in general more reactive than D block elements. Some of their chemical characteristics are: they tarnish readily on exposure to air. In finely divided state, all burn in air to form co-oxides of the formula Ln2O2O3, where Ln stands for lanthanide, except cerium, which gives CeO2. Yttrium, however, resists the action of air even at 1000 degrees Celsius due to formation of protective coating of its oxide. All react with water slowly in cold but rapidly on heating, liberating hydrogen and forming LnOH thrice. All this combined with hydrogen at 200 to 300 degrees Celsius, giving LnH3. They also combine with halogen, oxygen and sulfur. They act as reducing agent for oxides of other metals. Cerium is used as a squenger of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of the formula Ln. Solubility of compounds. The fluoride oxides hydroxides, carbonates, phosphates, chromates, oxalates of lanthanides are largely insoluble in water. On the other hand, the lanthanide other than fluoride, nitrates, acetate, perchlorates, and salts of oxoacids of lanthanides are soluble in water. The solubility behavior of salt of lanthanides follows the pattern of solubility of salt of group second elements. However, lanthanide sulfates, unlike the sulfates of group second elements, are soluble in water. 9. Tendency to form complexes. Although the lanthanide ion have very high charge +3, yet they have large size of their ion compared with the transition metal. As a result, they have low charge density and therefore they have very less tendency to form complexes. Their complexes with unidentate ligands are very few and form complexes only with fluorine and oxygen donor ligands. However, they form complexes with a few chelating ligands such as beta diketones, oximes, ethylene diamine tetraacetic acid, EDTA, alpha not dipyridyl, and hydroxycarboxylic acid such as citric acid. These complexes usually have high and variable coordination numbers, and water or solvent soluble molecules are often attached to the central metal atom. Beta diketone complexes of EU3 positive and PR3 positive dissolved in organic solvents are used as lanthanide shift reagents in NMR spectroscopy. In contrast to transition elements, the coordination number 6 is very common. Coordination number below 6 is also uncommon and occurs only when bulky ligands such as 2,6-dimethylphenyl negative and NSIMe3 hold twice ligands. However, coordination number 7, 8, 9 are common, and these gives a variety of stereochemistries. For example, the coordination number 4 LNOH2 N whole plus 3 is in aqueous solutions are thought to be 9 for earlier lanthanides and 8 for smaller members of series. However, these ions are highly labile, and smaller yttrium ion YB3 positive forms 7 coordinated complex, and larger La plus 3 is 8 coordinated. The structure of these complexes are a capped trigonal prism and a square antiprism. The coordination number 10 and 12 occurs with a larger lanthanide and small chelating ligands such as NO3 negative, SO4 2 negative. Ce4 positive is smaller and highly charged and forms CeNO3 6 whole 2 negative in the aqueous non-aqueous solution and 2O4. This is 12 coordinated Ce in which each NO3 negative ion uses 2 oxygen atom to coordinate to the metal. When two trans nitrates of these complexes are replaced by PH3PO, it gives 10 coordinated orange colored neutral complex CeNO3 4 OPPH thrice whole twice. The sulfates FeSO4 twice NH2O and NH4 twice CeSO4 thrice and iodates are also known. Large number of salts of organic acids such as oxalic, citric, tartaric have been studied mainly for separation method. These ions have chelating oxygen ligand forming complexes with aln3, unidendant O donors such as pyridine and oxides, and triphenyl phosphine oxide also forms many complexes with lanthanides in +3 oxidation state. The complexes with ligands such as an EN, diene, bipyridine, tetrapyridine can be prepared in polar organic solvents. As with other transition metals, the lanthanides can be included to form complexes with exceptionally low coordination number by use of bulky ligands. This is an example of coordinated number 3, which is the lowest found for lanthanides. They are volatile, air sensitive, and easily hydrolyzed. They are planar in solution but pyramidal in the solid state. With PH3PO, the 4 coordinated distorted octahedral adduct. Lanthanide also form two main types of organometallic compound. First is predominantly ionic cyclopentadienides and second is sigma bonded alkyls and aryls. These type of compounds are usually thermally stable but unstable with respect to air and water. In polar solvent, these complexes are solvated and are monomeric, but in non-polar solvent, the tris C5H5 compounds are insoluble while the bis C5H5 compounds dimerize. The lanthanide also form alkyls and aryls by metathesis in THF or ether solution. Triphenyl and polymeric, in which aln is tetrahedrally coordinated to 4 sigma aryl methyl aryl group methyl derivative have been obtained. Octahedral LN-Me6 whole 3 negative species of lanthanide have been isolated. In contrast to transition elements, the lanthanides do not form complexes with pi bonding ligands such as CO, NO, CNR, etc. The difference arises because the 4f orbitals are well shielded and are inside the atoms. Therefore, they cannot take part in sigma in pi bonding, whereas in the transition elements, the d orbitals are commonly involved in pi bonding. Double bond formation. The lanthanide salts form double salt with corresponding salt of ammonium and alkali metal. Double salts like alum with 24 water molecules are not formed. This is because the lanthanide ions are so large that these cannot coordinate to 24 water molecule octahedrally as in amyl. Thank you.